We call nucleophilic substitutions SN reactions, S for substitution, N for nucleophilic. And there are two types of nucleophilic substitutions, SN1 and SN2. And 1 and 2 refer to the kinetic order of the reaction. In SN2 reactions, as a bimolecular reaction order, it's an order 2 reaction order, the nucleophile is entering the molecule and the leaving group leaving the molecule at the same time. Everything happens simultaneously, and that is what is that's why it's a reaction order 2. It depends on both players, the substrate, the one that the electrophile, the one that is going to have the leaving group and the carbon with the partial positive charge, and the nucleophile, the one entering the molecule. What sort of factors affect a nucleophilic substitution 2? Well, on one hand, the concentration, and it depends on both concentrations, the concentration of the substrate, the compound you are making the reaction on, and the concentration of the nucleophiles. The pH, the presence of protons. You do not want hydrogen ions, or you don't want in the medium, because the nucleophile might react with those hydrogen ions, be attracted to those hydrogen ions rather than to your substrate, the substance you actually want to do the reaction with. It's also affected by steric effects, steric hindrance. The nucleophile needs to be able to approach the carbon in which there is going to react. And it's a carbon that is going to be surrounded by substituents, because the nucleophile enters the molecule at the same time as the leaving group leaves. So it is necessary for the nucleophile to have a physical space in which to attack that nucleophile. And it also affects, it's also affected by nucleophilicity. How good the nucleophile is in the first place, and how much affinity it has with the substrate, rather than, for example, hydrogen atoms, both from the solvent or from other parts of the molecule. So all those factors will play an effect on a nucleophilic substitution 2, on an SN2 reaction. An SN1 reaction is a first order kinetics, and it happens in two steps. In the first step, the leaving group leaves before the nucleophile attacks. In this case, I've got here the example of a chlorine that is going to be the leaving group. This is the electrophile, the electrophilic carbon, and this is going to be your nucleophile. And the first step of the reaction is the chlorine atom in the form of chloride leaving the substrate. So you form a carbocation intermediate. And in a second step, the carbocation intermediate is attacked by the nucleophile and the final compound is formed. And we call it first order kinetic because the speed of the reaction is going to depend exclusively on how easy, how difficult it is to make that carbocation intermediate. So it depends on the substrate. If the substrate is able to form that carbocation easily, if the leaving group can leave the molecule easily and that carbocation can be formed fast, then the reaction will go fast. And if the more difficult it is for the leaving group to leave, the more difficult it is for the carbocation to form, the more unlikely is that that reaction will happen as a first order kinetics. Once the carbocation is formed, because it's a positively charged carbon, it's a very powerful electrophile, it has very strong tendency to react, the rest of the reaction happens very quickly. So that is why it's a first order kinetic. It depends exclusively, strongly, fundamentally on that first step, the leaving group leaving the molecule. SN1 reactions tend to happen when you have a central carbon atom surrounded by bulky groups. On one hand, because if you have bulky groups around your electrophile, your carbon with a partial positive charge, then it will be difficult for the nucleophile to attack. So an SN2 reaction will be difficult. There is no space for that nucleophile to attack the carbon. And also because when you have a highly substituted carbon, then that carbocation is more stable. So it will be able to stabilize that positive charge more easily. So it's more likely to form. Sometimes SN2 reactions are called dissociative reactions. So people talk about dissociative mechanism, and that means that, what we mean with that is that the leaving group dissociates completely from the molecule. It leaves the molecule completely before the nucleophile attacks. Let's have a look at the stereochemistry of nucleophilic reactions and the different products, stereochemically speaking, we can get when the mechanism is an NS1 or an SN2. Let's first look at nucleophilic substitution 1, SN1s. When we have a nucleophilic substitution going through an SN1 mechanism, we have the substrate we are using is an optical isomer, it's an stereoisomer. It has a chiral center. We're going to have a mixture of both enantiomers as the product. So the stereospecificity is lost in the reaction. Why is that? Because the reaction goes via the formation of a carbocation. Let's look at, for example, this example. When the first step is the loss of the bromine atom and the formation of a carbocation. And when the carbocation is formed, that sp3 carbon that was a tetrahedral carbon and it had a particular stereochemistry becomes temporarily an sp2 carbon, and it has an empty orbital, which is the one that is going to be attacked by the nucleophile. And in this case, the nucleophile, the molecule of water, can attack or on one side or the other side of the molecule. And it will roughly attack with a 50-50% chance of forming both, it's a 50-50% chance of either attack happening. So as a result, while before we had one enantiomer, the product of the reaction will be the two enantiomers, because there's no preferred attack of the nucleophile on one or the other side of the carbocation that has been formed. And another image of the stereochemistry of a nucleophilic reaction when it's an NS1, because the carbocation form is a planar structure, it's an sp2 hybrid. The nucleophile is free to attack from either side of the molecule, and both stereoisomers, both enantiomers, will be produced. We call that a racemization of the chiral carbon, of the asymmetric carbon, because you end up with the two possible enantiomers for that particular carbon. Let's now look at the stereochemistry of SN2 reactions. In an SN2 reaction, the nucleophile enters the structure at the same time as the leaving group leaves the structure. That means the nucleophile cannot attack on the same side as the leaving group is, because that would not allow the leaving group to leave the molecule. It needs to attack from the other side, the opposite side to where the leaving group is. That means that when you have an attack in a carbon that is optically active, a chiral carbon, an asymmetric carbon, the resultant product will have the opposite, the inverted configuration with respect to the reagent, because the nucleophile will be attacking on the opposite side to where the living group is, so you will end up with the opposite configuration, an inverted configuration. So as a summary, in SN1 reactions, because they happen via carbocation, the nucleophile can attack from both sides of the carbon, and there are two possible enantiomers to form from that attack. And in SN2 reactions, when the reaction happens on a chiral carbon, the product will have the inverse configuration to the reagent, because the nucleophile will attack on the opposite side to the leaving group.